Welcome back to Built Fabrications and the second episode in the 383 Basics series. And today we're going to be discussing rod length and balancing.
You can see the riding on the pavement. Young kids, they're growing up in basements.
I'm actually going to address these two topics in reverse order from how I have them written. I'm going to start by talking about balancing, and that's the balancing of your rotating assembly. And what that means is, in the last episode we addressed, what a crankshaft is, connecting rods, pistons, when we were talking about our compression ratio. And so whenever you have an engine running, you want the forces of the weight, it's called bob weight. You want the bob weight of your piston and your connecting rod to be equal to the weight that is in your crankshaft. And this part here is called the counterweight of the crankshaft. And I could show you that here on a crankshaft in a minute and kind of go into some detail on that. So the reason why you would want those forces to be equal is because whenever you get into higher RPMs, any off weight or off balance in your rotating assembly will cause vibrations, and having vibrations for a long enough period can result in damaging parts and also just not a good ride. You'll feel the vibrations running through the vehicle, and the longevity of it will not be as long as if it was balanced. So looking at this crankshaft, you can see this half moon is the counterweight, and it's always going to be 180 degrees out from where your connecting rod would be. And so the counterweight is actually going to act against the connecting rod and the piston to balance out that bob weight. So as the engine runs, the crankshaft is going to be rotating, and the point at which your piston and connecting rod are at top dead center, which is the farthest point up in the cylinder that it travels, the counterweight is going to be 180 degrees out from that. And they're going to, ideally, if it's a rotating assembly, the weights of them are going to be equal, so therefore they should cancel each other out. So you shouldn't have any vibrations in a perfectly balanced system. A perfectly balanced system isn't something that you're likely going to achieve, but you want to try to get that bob weight or that balance to be as equal as you possibly can to reduce any vibrations that you would possibly get from having them offset. So an old school 383 stroker would consist of replacing the crankshaft out of a 350 Chevy with the crankshaft out of a 400 small block Chevy, and you would turn down the journals, the main journals on the 400 crankshaft to fit the journals on the block of the 350. And you would use that crankshaft with the stock height connecting rods as well as pistons in the 350 Chevy, and that would essentially give you the 383 stroker. So with all 400 small block crankshafts, they were all externally balanced, meaning you had weight on the front and the rear of the motor to balance out the bob weight, like we discussed previously, of that engine. And the reason why it was externally balanced is because there was not enough clearance inside the engine block to have the additional weight in your counterweight on your crankshaft without it hitting the piston or hitting the block. So the engineers at GM had to come up with a way to balance it, which resulted in using a balancer on the front of the engine, and then also adding or reducing the weight to your flywheel or flex plate, depending on if you had an automatic or manual transmission, on the back of the engine. And I have a flex plate here with me that I could show you, as well as a harmonic balancer. It's also sometimes called a damper, and I'll show you what those two things are so you can kind of have an idea if you don't know already. So this is a harmonic balancer. And the difference between a harmonic balancer and a damper is they're really the same thing. The only difference being that a harmonic balancer typically has weight to offset or to help with the balancing of the rotating assembly, whereas a regular just damper would just dampen any vibrations in the rotating assembly, but not necessarily address any balancing issues, and it'd be something called neutral balanced. So this would sit on the front of the engine on the snout of the crankshaft, and it would take care of the balancing for the front. And then for the rear, this is a flex plate. I don't have a flywheel with me on hand, but a flywheel essentially is very similar. It's just the way that it contacts with the clutch versus this would be bolted to a torque converter, but I don't want to get in the weeds on discussing the difference between those. But this would be on the back, and typically with a flex plate, you would have a counterweight that would be welded on this that would be opposite to usually the connecting rod and piston, or always the connecting rod and piston, because that is typically going to be heavier than whatever your counterweight is. And if you have an externally balanced engine, it's almost always going to be because you couldn't have a large enough counterweight to fit inside the engine without having any contact or clearancing issues. With the popularity of the 383 stroker, manufacturers started developing 383 specific or purposed crankshafts for engines, so that way you don't have to turn down the journal sizes. And there's two different ways or two different crankshafts that you can get for a 383 stroker, and it's internally balanced or externally balanced. The difference being an internally balanced crankshaft has all the balancing is done inside the engine block, and you don't have weight mounted to the front or rear like we just discussed, which would be an externally balanced engine in that case, where you'd have the harmonic balancer on the front and then added weight on the flywheel or flex plate, or reducing depending on whatever way that you set that up to do that balancing. So the two main factors that are going to play into whether you run an internally balanced crankshaft versus an externally balanced one are going to be the issues of price point and clearancing. And so the pros of running an externally balanced crankshaft are that they're typically always cheaper because they are easier to clearance, because you have the weight on either end of the crankshaft, so you don't have to worry about a lot of the clearancing issues that you would have. And the materials to do that balancing are typically also cheaper than how you would have to configure an internally balanced crankshaft. Now, the downsides to running an externally balanced crankshaft are that the balance on them typically isn't as good as an internally balanced engine. And also, while it's not a very, very common issue, you do run the higher risk of breaking the crankshaft, especially if you're going to be running at higher RPMs, having the weight on either end of that crankshaft. It increases the risk for something to go wrong. So you're probably saying to yourself, well, I don't want that. I want to go with an internally balanced crankshaft then. And ideally, in a perfect world, you would, if the price point's right and really the clearancing is going to just play into price point. So there are a few different ways that you can accomplish having an internally balanced crankshaft. And a few of those could be reducing the weight on the on the rod journal side of the crankshaft, or another way, you can drill out the counterweight and add a material. It's a metal called Mallory, and Mallory is very dense, very heavy material. However, the downsides to Mallory is that it's very, very expensive. So depending on what your bob weight is and how far out your weight is, which again is the combined weight of your connecting rod, piston, wrist pin, rings, all that, compared to what your counterweight is going to be, you're going to have to add more Mallory the more that is off. And that could get very, very, very expensive in a hurry. So the other thing that makes it a lot easier to be able to run an internally balanced crankshaft nowadays, though, is the materials that we have and that we use, or manufacturers use, to make internally balanced crankshaft. Typically you can make them lighter or heavier as you need, but the most common thing that you're going to run into with an internally balanced crankshaft is going to be a 6-inch rod for your connecting rods. And the reason that you would need that 6-inch connecting rod is because, if you see, the reason why you have this crown on your piston, which I could show you here, the reason why you have this clearance in here on the skirt is not for some looks or aerodynamics or whatever you want to call it, but as this piston gets to the bottom of its stroke, it runs very, very, very close to your counterweight, which that is going to be one of your biggest points of clearancing that you run into where you have a problem having an internally balanced crankshaft. So the more weight that you put on your counterweight, the larger it's going to be, naturally, right? So if you go any bigger, in a lot of cases with the standard stock connecting rod and piston height, you run a major risk of having your piston contact your counterweight on your connecting rod, or your crankshaft rather, whenever it's in the bottom of its stroke. So the way that you can kind of get around that is with your connecting rod length. So just as a little quick disclaimer, I probably don't have to mention it, but none of these drawings are dimensionally correct or to scale. And please give me a little bit of slack. I've never claimed to be an artist, so I just want to specify that before I get into especially different lengths. But if you look over here, I have a theoretical 5.7 inch connecting rod, which is the stock rod length and piston that you would have in a 350 small block Chevy. Compared to next to it would be a 6-inch connecting rod. And if you look, the difference between them is you can take and move the wrist pin in the 6-inch connecting rod higher up on the piston, and by doing that you can trim off a lot of the length of the piston, which will give you clearance. And the added weight that you'll get from the longer connecting rod is offset by the weight that you trim on that piston. So they kind of balance each other out. Because, you know, whenever I was first doing this, I wondered, well, hey, if you're adding a longer connecting rod, there's more material, therefore more weight. So, does that mean that it's going to throw off your bob weight real bad? And the answer is no, not really, because of, like I just mentioned, having that wrist pin higher up, you don't need that additional material on the piston. So you would be moving this wrist pin here up pretty much right under the ringland, the bottom ringland for your oil scraper ring, and you can trim off a lot of the length. So you have a shorter piston and a longer connecting rod. So what you can accomplish with that 6-inch connecting rod and piston, with it being shorter, is you can now add a little bit more weight and material in your counterweight on your crankshaft. And again, this is just a really crude drawing, and you can add that additional weight without running into clearance issues, or as many clearance issues as you would with the 5.7 piston and connecting rod, because you move all this up, so therefore you put more material in there. An additional benefit that you run into with running a 6-inch connecting rod versus the stock 5.7 rods is that whenever you increase the stroke, like we did going from a 3.48 stroke on the crankshaft to a 3.75 to get the 383 stroker stroke, whenever you have that shorter rod, you're bringing it lower in the cylinder, and by doing that, you're increasing the angular forces of the piston, the piston side load against the cylinder, which puts more strain on everything. You wear out the skirt, which is the side of that piston, where it goes up and down in the cylinder wall, on the cylinder wall. You run the risk of running that skirt out quicker, as well as just putting additional strain that's not necessarily necessary in your connecting rod and piston wrist pin. So having a longer connecting rod takes off some of that load, where as you came down with the shorter connecting rod and it'd be at a steeper angle, having a longer connecting rod adjust for that, because it brings it up. Since you're moving the wrist pin up higher, it can adjust for that, so you don't have as much piston side load or angular forces against the cylinder wall, potentially damaging the skirt or breaking a wrist pin or connecting rod. So I have a connecting rod and piston here, probably be a much better visual than marker. So theoretically, with a 5.7 rod, as you get to the bottom of the stroke and you bring that lower in that cylinder, you're running at the steeper angle here. So the angle of your connecting rod is going to be, say, theoretically like this, and it's pushing against the cylinder wall, versus having the longer connecting rod and bringing the wrist pin up. It's still the same overall length, but having it higher, instead of being at this angle, it will be a little bit more like this, where you don't have as much of a force going on the side, which this is the skirt of the piston, and you can see where the wear pattern is, and that's typical. Like, you will get wear on the skirt, but having more of a load is going to increase the rate in which, especially the one side that is going to be on pushing against the cylinder wall, is going to wear out faster than if you otherwise would be at a stock stroke with this setup or running the 6-inch connecting rod. It's important to be vigilant whenever you're sourcing parts for a 383 stroker build, that you make sure that everything is designed to work with each other. So a lot of times you might come across an internally balanced crankshaft where it will be advertised as that, but it will say that it is a 6-inch, meaning a 6-inch connecting rod crankshaft. And you cannot run 5.7 pistons on that. So although it's internally balanced, you run the risk if you run, a 5/7 piston and connecting rod with the 6-inch crankshaft, you run the risk of having contact and they will not work together. So if it's specified as an internally balanced 6-inch crankshaft, you need to make sure that you have that set up for it. And also, whenever you're going to be doing that, you can't just replace the crankshaft and keep the same piston and rods for the stock 350 Chevy, the 5/7 connecting rods and piston. I mean, if it's a internally balanced crankshaft that's designed for 5/7 and you have to verify that, then it's okay and you can use the original pistons and connecting rods. But if it's not, you need to then get the 6-inch connecting rod, and if you're not getting a rotating assembly and you're getting your pistons and your connecting rods and bearings and crankshaft all separate, you need to make sure that you get 6-inch connecting rod pistons as well as your 6-inch connecting rods, because you cannot use a 6-inch connecting rod with a standard size piston, because you're going to raise the piston, because the wrist pin is not going to be at that heightened point in a regular piston, so therefore your whole system's gonna be taller and you're gonna run into all sorts of problems. You'll have a lot of clearance on your counterweight here, but then you're gonna ram that piston right through your cylinder head. So don't do that. Be vigilant, make sure that everything goes together. Ideally, it's gonna be a lot easier, especially if this is going to be your first time or one of your first times building an engine, especially a 3-3 stroker. I would highly recommend going with a rotating assembly that someone already pre-packaged and decided or determined that everything goes together, as well as the bob weights and the balancing of all those components are together. Because piecemealing the parts, you're going to run into potentially big issues trying to get your crankshaft balanced, whether it's, especially if it's internally balanced, but even externally balanced. Because your weights, you can have really heavy connecting rods or a heavy piston, or a heavy connecting rod, light piston, where this crankshaft that's internally balanced, theoretically, for something else, for say, a light piston and a light connecting rod, if these are out of spec for what this is balanced for, an internally balanced crankshaft, it's no longer internally balanced. Now you have to go and send that out again to a shop to get it balanced, machine shop, and you're going to run into problems where you have an internally balanced crankshaft where you potentially spent more money on it already, and then you're still going to be in the same boat of having to add Mallory or trim, and you just don't want to do that. So a pre-set up rotating assembly is probably going to be the best route to go. If you really are adamant about having a certain piston or a certain connecting rod with a certain crankshaft, consult your engine builder, your machine shop, whoever's going to be doing a lot of the work for all your clearancing and oversizing your cylinder, and discuss with them the different things that you want to do and try to find a solution to see if you can even internally balance that setup and how much it's going to cost to do that, and weigh your options. So with that, we pretty much touched on all the main points between 6-inch and 5/7 connecting rods and pistons, as well as bob weight and an internal versus externally balanced crankshafts. The main takeaway, 6-inch connecting rods are going to probably be the main goal or the main route that you're going to run if you want to do an internally balanced crankshaft, where all the weight is on the inside. An externally balanced crankshaft, they're still great crankshafts. They're the way to go if you're on a really tight budget, and they're definitely a lot simpler to do. You're not going to have to change out pistons and connecting rods and everything. You can use, just besides the difference in cost between the crankshaft and with having to balance it, you can run your stock pistons and connecting rods. So it's going to be a lot simpler in that aspect. So hopefully all this helped you guys out, helps you understand a little bit between the differences between the 5/7 and a 6-inch connecting rod and why. And again, I can't stress enough, make sure everything is spec'd for one another, and keep in mind that changing any component is going to change your bob weight or the balance that you have on your rotating assembly. So you need to make sure that whatever you add or subtract from your pistons and connecting rod setup is going to be equally reflected in your counterweight or your externally balanced weights. So get outside, get wrenched on something, piss off your neighbor, disappoint your mom, and until next time, keep on keeping on.
You can see the riding on the pavement. Young kids, they're growing up in basements. Online, a whole new generation. I'ma make mine, so you better go take it. Always, they need a new replacement. Decentralized, can't contain it. We're changing lives, yeah, upgrading. Call it suicide of the older generation. What keeps you up at night, yeah.